check. Okay.
Okay, CQDX, CQDX. At CQ Delta X-ray. CQ Delta X-ray.
Morning, Critter.
Charlie X-ray Delta, QSDX.
Adirondacks, if you're listening, 20 meters looks pretty open.
That is the left signal calling. Please repeat your call, over. Ocean Delta Delta is approach, over. Okay, over.
Calling on a CQ20 meter, PCC to the Whiskey 2, Charlie Lima Mary, calling as Danny by over. Going for Yankee Radio. Go on, Tony.
Okay, thank you very much. Thank you very much.
We were south of the Falkland Islands, I think this morning or late last night. I gotta see on the buster they were doing some QSO with the digital mode FTC. I don't have anything with digital, and I'm not able to do any digital transmission, so unfortunately not blocked for me to get in contact with the ship. I'm gonna move down to South Africa in a few days, and I'm probably gonna be there, and not so sure if I'll be able to go through the pilot with my setup down there. I'm just running an old Icon 728 and a vertical antenna with only 100 watt, and I'm about to pile up to go through the Bouvet Island. The X expedition will be quite hard to do. Unfortunately, I'm leaving from here where my setup will probably allow me more chances to the X expedition, but by being there, the chances are going to be very small. So I'm not sure when the boat will reach Bouvet, but I assume another day to use my ship. I think they were just out of Falkland and going about 12 miles an hour, so it's going to be a long week for the guys down there. So back to you, Craig, at GW9R, how you doing?
All right. I'm going to see if my
Maybe like go somewhere where there's not so much okay, and that's Long Island, and Long Island is just a straight Charlie calling CQ Dog X-ray, Lima, North America. India 1, Canada, Hotel Canada calling CQDX, CQ Dog X-ray, Lima, North America. Italy 1, Charlie, Hotel Charlie calling CQDX, CQ Dog X-ray, Lima, North America. Italy 1, Charlie, Hotel Charlie calling and listening. Kilo Mike 4, Delta Lima Golf, is that correct?
great. Another appliance operator.
Kilo Mike 4, Delta, question mark golf. We're in the middle edge of the traffic.
All right. I don't feel like listening to that anymore. Anyway. Going mute, too much noise. Ha ha ha. All right, fine. Whatever. I'm going to see if this cassette tape head demagnetizer will demagnetize my tools. And yes, it did. Sweet. Relatively speaking. Yeah. MPF 102. Wow, I got a bunch of these. Why did I buy all of these? I don't know. You know, all three of the women in my house had a cold 2 weeks ago. The cold came and went from my house. I managed to steer clear of it. And god damn it, I picked it up and brought it into the house again. From outside somewhere. Pisses me off. $2N54.84. My oldest daughter, who's the nurse, had it for like 3 weeks. It hung on to her. You had snow there? In England? I didn't think you guys had snow. That's a 2N5432. Looks like these are all 5432s. Stud mount? I don't think so. Drain to source on resistance, 5 ohms max, really. Oh God, I'm gonna sneeze again. God damn it. Drain source. gate. So if I short the gate, oh no, source is that one. So if I short the gate and the source together, that's 0 volts. Then my resistance from the source to the drain should be 5 ohms. And it's very low. That sure looks like 5 ohms to me. Wow. All right. And if I disconnect that, goes up. All right. Yeah, you can thank my wife for that. I thank my wife all the time for that. She spent a good chunk of change on this chair that she bought me. It's really nice. It has a very large height adjustment range. The only thing it doesn't have that I wish it had is I can adjust the backrest height, but I can't adjust how far the backrest is from the seat. I'd like to move it back just a little bit more to get more of my thigh up onto the seat. If I had my druthers, that was probably another $150. VCR 4N. What is that? Let's see. VCR 4N. Data sheet catalog. A voltage controlled resistor. Oh man, this is exactly the MOSFET the JFET that I want. Holy crap. VCR, voltage controlled resistor. Look at that. That is exactly the MOSFET I want. I should say JFET. That's awesome. Gate to source cutoff voltage, 8 volts. It's 25. Gate to source cutoff voltage. To 600. Ham band's bad. I don't know. 20 meters seems pretty open to Europe right now. Glad to see the IHC still. I don't even know what is an IHC. Oh, induction heater, sir. Okay. You're starting to sound like Shubis here with all his acronyms. Yeah, let's melt shit. Yeah, well, let's melt ship and not have it blow up. that's the key here, because I'm going to be the next step is to power this circuit up from 240 volts, and yeah, I don't want sparks. All right, source, drain, gate. Source, drain, gate. Alright, so between the source and the drain, between the source and the gate, on 1 mega ohm. Come on. Alright, source and gate 1 mega ohm. Source goes to ground. send an input voltage to the gate through $10K. Sure, why not? $10K. So this will be my input signal to the gate. It needs to be a negative voltage. It'll be another year of regular work, but videos of getting a road established, yep, and maybe a shed built. Nice. I started to get the old symptoms, cold symptoms a few days ago. Negative voltage, huh? You know, something doesn't make sense to me. Let's just breadboard it and see what happens. have to draw this out. This doesn't make sense. An NPN transistor has a negative ground, right? So a positive voltage here forward biases the emitter base junction. Oh. The whole idea of this transistor is to reverse bias the gate to cause it to open up because the normal state is on. It's the inverse of a bipolar transistor. So if I want to reverse bias a JFET with a positive gate voltage, I need a P channel. Shit. That's right. Alright, who wants me here? Zero fossil fuel. I really think this video will help regarding JFETs. Getting a shipping container on the property here would solve my space problems. JFETs are completely different to a transistor. Yeah, I know. Shipping containers are heap here. They want about $2,000 for a smaller one. I'm looking at like $1,500 for a 20-foot. That's a good price, critter. Yeah, it depends on location. Turn the JFET off. You often need a minus voltage below. Yeah. Just saw them on Craigslist. Okay. Yeah. All the JFETs that I have in my parts drawer are all N channel, so they require a negative gate voltage to turn them off. So I either need to use P channel or I need to go to a split power supply with plus and minus voltage rails. And guess what? I'm not going to do that. So the question is, can I easily get a negative voltage? You know, I can probably get a negative DC voltage to bias the JFET from the AC signal that's coming off of the oscillator. Let me think about this. Well, call it what you want. Yeah, that's probably we're talking about the same thing here. Yes, I think that will work. I can compensate for the half voltage, the half wave rectification voltage loss in the gain of the error correction amplifier. That will work. So I've got my square wave coming in, and this is 0 volts. We'll call this 10 volts. We'll send that through the capacitor. With a diode to ground. Let's see. That will give me a positive voltage. No, I want a negative voltage. Like that. Diode isolate it, filter it, and there's my negative gate control voltage. All right, problem solved. But the question is the voltage proportional to the duty cycle? Do I care? No, it only needs to hit a threshold. It only needs to hit a certain threshold. Duty cycle is taken care of by the chip. All right. I don't want to overthink this. Right. So we'll do about 10 microfarads to ground. Diodes. There's one. There's two. And what do I want for input? We're going to be looking at about 50 kilocycles, so I'll go with 0.05. That should be good. There's my input 1. And input ground. Right. And then, let's see, gate, drain, source. Alright, so my input voltage oh, that's wrong. would not have worked. Source is closest to the tab. Oh. Source, drain, gate. Yes, that would have worked. Source, drain, gate. Source, drain, gate. And the source goes to ground. I can't believe I had this JFET in my parts drawer. That is a major win. Alright, so there's my signal input. There's my signal output. And my common ground. Right there. Alright. If I check this resistance to ground, I should see about 600 ohms. Anywhere between 200 and 600 ohms. 200 is the minimum, 600 is the max, and I'm seeing 327 ohms. That's a beautiful thing right there. Six different JFETs, very informative tests. All right, I'll look at it.
Good morning all, and a Happy New Year. It's 2018, it's New Year's Day. And I thought you'd like to watch me play with some transistors. So what I've got here is a little tiny breadboard, 9-volt battery and an LED. Of course, I'm not going to connect the LED directly to the 9-volt battery because that would kill it. No, I'm going to connect it through 2 pins of this little transistor. So let's put that in there, and well, nothing's happening. But if you wait a while, that LED gradually comes on, which is quite interesting. And if I move my hand near the transistor, like so, and then pull my hand away, the transistor sort of conducts and then doesn't conduct and does weird stuff. Now, if you're thinking, well, it's doing those sort of weird things, responding to my finger coming closer and moving away because it's a FET, well, you'd be right, this is a FET. This is a field effect transistor. It's not a MOSFET. It's not even an IGFET. It's not an insulated gate field effect transistor. This is actually a JFET. It's a junction field effect transistor. And the gate, which is on this right-hand side, not connected to anything, the gate here is a PN junction. It's P-type semiconductor material attached to the gate, and there's some N-type semiconductor material connecting the drain and source together. Now, although it's a PN junction, it's very sensitive to electric fields. This is either induced or capacitively connected or something like that. The transistor turns off to flow through this PN junction, so I've got to limit that current, that's why I'm using a 10k resistor. Connect that up to this positive voltage up to the electric field on the gate, 1.5 volt battery to electric fields. So let me desensitize it by connecting the gate to the source through a 100k resistor. So that now means that there's a leakage path away from the gate. So the gate is at the same electrical potential
The only problem I have with his circuit right there is if he had a low RDS on JFET, that would pop the LED and the JFET.
As the source is there in the middle, drain is up here on the left hand side. And now I can do a couple of things. If I get some voltage, so I'm going to use this 1.5 volt battery, and I take the gate negative, so here's the gate, let's take it negative with respect to the source, I can turn the transistor off. So this is a depletion mode transistor with no voltage on the gate. I've got my resistor connecting gate to source. The transistor actually conducts electricity. It's got a moderately high resistance because the LED is not that bright. If I put a negative voltage on the gate, like so, it pinches off the N channel, the channel between drain and source, which is allowing current to flow. If I put a negative voltage on the gate, it pinches it off. Now notice I'm not using any current limiting here. I'm connecting this battery directly between gate and source, and that's because if I reverse bias this PN junction, no current flows. So actually this transistor is responding to just the electric field by having 1.5 volts put on the gate, and that pinches the transistor off, turns it off. However, I've also noticed that although this is a depletion mode device, if you connect the gate, and this is a 10k resistor, the gate to a positive voltage, now that will allow current to flow through this PN junction, so I've got to limit that current, that's why I'm using a 10k resistor. But connect that up to this positive voltage up here, then masses of current flows through that N channel. I'll draw this because it's not obvious what's going on by looking at this, but I can kind of run this in enhancement mode by taking the gate positive with respect to the source. It enhances the channel through which current is flowing, and far more current flows. Still not enough to burn the LED out. There's no resistors in here. There's certainly no resistor in the path of the LED. I'm simply relying on the resistance of the N-channel semiconductor material in the transistor. I can enhance it, or I need a separate source of voltage for this. I can deplete that channel, I can pinch it off, and the transistor turns off. Interesting device. So here's a datasheet for the 2N5457, that's the JFET that I'm using. And it's got a very interesting symbol. It's an arrow, which is a PN junction. Here's the N channel, this is N-type silicon, running between drain and source. And you'll notice it's completely symmetrical. The gate arrow comes down into the middle of this N channel. And in fact, this device is completely symmetrical. Drain and source are completely interchangeable. It's not like the collector and emitter on a bipolar transistor. And just to demonstrate that, let's take out this 100k resistor so that the gate becomes susceptible to electric fields again. And I've got another one of these 2N5457s, which I've bent the gate connection out. So let's take this one out, put this one in, and as you see, again it's susceptible, but if I leave that, because of leakage, whatever voltage is on that gate, it's probably a negative voltage because it's pinching off the N channel. Because of leakage, that voltage decays away and the channel conducts. Now if I turn that round, so drain and source are opposite ways round, it just does exactly the same thing. A negative voltage got induced onto that gate. If we let that drain away, it just conducts through that N channel. Drain and source have no actual real polarity meaning. They're completely interchangeable. In fact, look at this. I've just printed out the datasheet for the J201 JFET, and you can see here it says, note, source and drain are interchangeable. So it's a symmetrical device. So let's just fold these over for a moment, and I'll just draw effectively what's inside this device. So we have a piece of silicon. It's doped. It's doped to N-type. That means that it's doped with a donor atom which donates electrons. So pentavalent, that means there are 5 electrons in the outer valence shell. 4 of those electrons make bonds with the silicon electrons, because silicon has 4 bond arms. It's all in 3 dimensions, so it's quite difficult to draw. But you've got a spare electron floating about, so it means now the doping levels are quite low. I was surprised. I've read that it's something like 1 in 100 million or something. 1 donor atom in 100 million silicon atoms. The donor atom is going to be something like phosphorus, which has the 5 electrons in the outer valence shell. So with this spare electron floating about, it's free to travel through the lattice, and it does that, of course, when you put an electric field across here. So across this N-type piece of doped silicon, we've got terminals. I don't know, this might be the drain, this might be the source, but of course it is. These are interchangeable. It's completely symmetrical. Now these metal legs are bonded onto the ends of the semiconductor material, so you've got an interface between metal and semiconductor. And I've been reading about this as well. I got very interested in all this recently. I've spent far too much time on this, really. These junctions, if you don't get them right, they can become rectifying because of something called the Schottky barrier. Now, of course, Schottky rectifiers are useful things, and Schottky diodes are made because they have certain properties which make them useful. But what you want here is not a rectifying junction, you want an ohmic contact between the metal and the semiconductor. And I think one of the methods of doing that is to heavily dope the region around where the contact is placed. I'm not quite sure what the doping level is on these JFETs. I think it might be moderately doped. But it's doped enough to allow electrons to travel through the lattice, through the atomic structure, and so an electron path is formed. Now, on here, we've got a couple of p-type regions, and they're actually connected together, and this is the gate. So there's kind of a piece of wire running around the back, connecting both sides together. When you put, so I should put a P there. When you put p-type semiconductor, now p-type is made by using acceptor atoms, so trivalent, 3 electrons in the outer valence shell, which means there's a missing electron, which means you've got a hole. And holes can conduct electricity in a different way, but they can conduct electricity as well as electrons. Spare electrons can conduct electricity. So N-type doped silicon conducts, P-type doped silicon conducts. However, when you put P-type doped silicon next to N-type, you get a depletion region. And in the JFET, it looks a bit like this. It's 2 sort of bits of depletion region punching in but not meeting in the middle. So there's still a channel for electrons to flow through here, even though you've got these depletion regions. These depletion regions are where electrons, the spare electrons from the N-type, jump into the spare holes, recombine with the holes in the P-type, and the whole thing becomes stable, electrically neutral, and it becomes an insulator. This region here, and it probably extends beyond there. So you've got this insulating area here, depleted region, which doesn't conduct. But there's still a channel through the middle which does conduct. Now, if you put an electric potential across a PN junction, and if you forward bias it, so you would put more positive on the P region, like a NPN transistor, you can get this region to shrink. So these 2 regions will shrink away, and that's what was happening when I was connecting the gate up to a higher voltage. These regions were shrinking back and actually providing a wider path through which more current can flow through this device. If you reverse bias the PN junction, and you do that by putting a negative voltage on the P region, these depletion regions actually grow, and they will grow to a point where they touch in the middle and completely block off this N channel. So if I induce a positive voltage, it's quite hard to do because as soon as you get a positive voltage on this P junction, the gate which is on this right hand side, of course the junction starts to conduct, so a positive voltage can't survive on there for very long. But I can just for very brief moments slightly enhance that N channel, but it's very easy to get a negative potential sitting on that gate, because now that the junction is reverse biased, it's a very, very high resistance, multi-megohms probably. That does leak away very slowly, and the N channel starts to conduct again. But like I showed, and in fact I can probably do it with the 100k resistor, if I take the gate more positive and hold it there, you get a really bright LED. I fixed the camera's exposure for this video because I didn't want it responding to the change in light level. If I take it more negative, and the only way I can take it more negative than the negative of this battery is to introduce another battery. Take the gate more negative, got to wait for it to turn on of course, then I can pinch off that channel and tell the transistor negative with respect to source, and I can, and that one does seem to go a lot brighter than the other two, so this one must have a much or slightly wider channel, which is allowing more A112 JFET, and it says here for the gate source cutoff voltage, minimum is -1 volt, and I've only got 1.2 volts with this battery, but the maximum is -5 volts, and they do apparently vary quite wildly between devices, so I might find another one that did cut off a bit flow, but by the same token it takes more voltage to pinch that channel to widen the depletion region.
Okay. I think we got the basic gist of that. In any event, I've got a signal generator up here. Let me run my test. Yeah, I know. It's just a nuisance. I am set to 50 kilohertz. $200k ohm scale. And if I do this, and this, I'm at roughly 300 ohms. And hopefully I've got enough voltage where I can turn the potentiometer and survey says no. Alright, so let's see what we've got for voltage here. -5 volts. So I'm able to go all the way up to minus 5 volts on the gate, and that's not enough to push me into the depletion region. Really? Really? All right. Let's crank it up here. My square wave, that's sine wave, that's square wave, doesn't really matter. So I'm through a 10K resistor. I'm able to go up to minus 6 volts on the gate. I'm on the 20,000 ohms scale now. Okay, well that's enough to do it. Hold on a second. What? Hold the phone here, folks. I think I have a problem with my breadboard. Son of a bitch. Oh, God. You know, I don't need problems like this. The reason I have Mylar tape on the bottom of this breadboard is because at one time I decided that I wanted to have all of the little power supply rails independent of one another. And then I later decided that was a bad idea, and I just jumpered it over with little solder bridges. But one of those solder bridges broke, obviously. The loose flubus. Oh, God. You know, I just don't need these kinds of problems. I need to buy some new breadboards. That's what I need. I need to buy some good ones. I think I'll maybe take a ride over to Cables and Connectors someday soon here and spend too much money and buy some halfway decent ones. keep them in business. All right, let's check this out again. So I should have 0 ohms now from here to here. Oh, that's sweet. Yeah. All right, trying this again. We'll start at 0 volts, 0 negative volts. I'm on the 20K scale. Got 300 ohms. And then if I start to increase the negative voltage to the gate, this should go up, and look at that. Ooh, wow, that's a very sharp region there where it goes up very quickly. It's very non-linear. Now I'm on the 200K scale. I guess there's a certain threshold. There's the 2 mega ohm scale. So it's pretty much open circuit with minus 5.38 volts on the gate. That's fine. I'm a little surprised how non-linear it is. To solve nonlinear, use a static fixed resistor and have trimmer parallel with that to overcome the sudden excess. Yeah, that would limit the range of voltage on the gate. Problem is each device will have a slightly different characteristic, like the guy was saying in the video. It's kind of interesting. Alright, so now I want to test that against an MPF 102, because the MPF 102 is stated as a switching device, but I don't necessarily know that it is. So let's check this out. Drain source gate. So it's the same. Oh, wait a minute. Drain source gate. This one is source drain gate, but if we're to believe the video we just saw, source and drain can be interchanged, so it doesn't really matter. So let's try plugging this in and see what happens. There's an MPF 102. Alright. Input signal. And my drain source resistance is infinite. And we drop this down. Oh yeah. This has a very sharp cutoff. Very sharp cutoff at minus 1.85 volts. And that too will probably work just fine. That's awesome. This test was a complete success. Activating the alarm. Well, you know, work needs to get my attention, and that works. As long as you don't abuse it, that's I'm okay with that. Alright guys, I think that's it for my test today. I might be back tonight, I don't know. I've really done a good job at catching up on my sleep. My daughter leaves for work at 2 o'clock, so I'm going to go up to the house right now and I'm going to have lunch. When my daughter leaves, my wife and I are going over to her house. We're going to screw the subfloor down. And yeah, I think that's it. Screw the subfloor down and check the water in the basement at her place. I should be back home for dinner, and after dinner I hope to be back down here working on the circuit. So catch you all later. Thanks for joining me. Hope you had fun. I will hopefully be back.